Hello everyone. So this is the live interactive session for week 9 of the course Structural Geology offered by NPTEL. And the topic of today's discussion is Boudinage and related structures. My name is Rajiv Mukherjee and I am currently hosting these live sessions for the course Structural Geology. So this is the course outline, and as per the schedule, we have already covered 8 weeks for the course Structural Geology, and for the live session for week 9, we have the topic on Boudinage and related structures. So this is the second part of the duration or the continuation of the previous week's content, which was mainly focusing on the ductile deformation of rocks and minerals. So in the previous week, we already discussed about the mechanism of folding and superposition of folding and superposition of deformation phases. And in this lecture, we will be discussing about Boudinage. Which is a form of ductile deformation, Boudinage, pinch and swell, porphyroblast, porphyroclast, etc. So this week's content is mostly focusing on the transition between brittle field and ductile field, or brittle deformation and ductile deformation. So we call it call these kind of deformation features that we generally observe as brittle ductile features or brittle ductile deformations. So it consists some plasticity or viscous element in the viscous component in the deformation, as well as there are signatures of brittle deformation, that is the loss of cohesion. So this is the 9th live session, and today is 21st of September 2024, and the live sessions are hosted on each Saturday 4 p.m. to 6 p.m. and this is the link to join the live discussion session. So let us move on to the course summary. So for summary of week 9, we mostly learned about, so the topics were twofold. That means in the first part of the week 9, we learned about porphyroblasts and porphyroclasts and their application in structural geology, how we interpret and utilize them. And the second part was mostly focused on the brittle ductile features such as Boudinage and pinch and swell structures and their details. So for summary of week 9, we mostly learned about identification, structural and petrological classification of porphyroblasts, difference between porphyroblasts and porphyroclasts, the relation between porphyroblasts and deformation fabric of the host rock, that is pre, syn, and post-tectonic or post-kinematic identification of porphyroblasts, utility of porphyroblasts in understanding the grade of metamorphism and association of metamorphism with deformation, if there is any. And we also learned about utilizing the porphyroblast as shear sense indicators. And then we went on to the second part of the week 9's content, that is Boudinage and pinch and swell structure. So the first part of these lectures were mostly focused on geometric concepts of Boudinage and pinch and swell structures, then classification of Boudinage and pinch and swell structure based on kinematics and geometry of the segments, formation mechanisms of Boudinage and its association with shear deformation, and geometric classification diagram of Boudins with relation to its occurrence, and aspect ratio of Boudins and its relation with strain ellipsoid and mode of deformation. So that rather talks about the deformation mechanism and stress and strain regime at which these kind of structures occur. And then we used, and then there was also some practical exercises involved in the week's content that are mostly to learn the basics of stereographic projection. So in the previous weeks, we already learned about the theoretical background of stereographic projection and how structural data are plotted on the stereo dates. But in this week 9, there was some additional practical exercises was also involved. So keeping in the summary for week 9, so this is the today's topic of discussion, which will involve some solving conceptual problems related to Boudinage and other little ductile structures, ductile deformation, and as well as some stereonet problems. So without further ado, just let us start our problem solving session for week 9 for the course Structural Geology. Okay, so the first question tells that which of the following microstructural features does not provide any information regarding the tectonic overprinting of fabric? Option A, xenocrysts. Option B, xenoclast. Option C, xenoblast. And option D, whiteinoblast. So I will give a minute to pause and then I will discuss. Okay, so when we talk about uh, deformation fabric or tectonic fabric, so this is important. Tectonic overprinting of fabric means the overprinting of foliation, right? So, for example, we have a clast. Let us say this is post-tectonic, right? Or post-kinematic. So if there is a clast which is post-tectonic, then we will see that the foliations will run undeflected parallel from the host rock into the clast or particle, let us say as particle, and then again host rock. Now, the overprinting relation would suggest that if this is a deformation phase, say D1, then if we have another phase of deformation, let's say D2, and another phase of non-coaxial deformation, let us say D2, which may suggest that this would run perpendicular to D1. So if this is D1, then definitely D2 would be perpendicular. So we are assuming that it is non-coaxial. That means there is a transaction between the two phases of deformation. So in that case, what will happen is that the clast will be overprinted with another set of uh, foliations, right? So with respect to D2, right? With respect to D2, the particle will be pre-tectonic, right? because it was already existing before the second phase of deformation, right? I mean, it may have grown after the first phase of deformation. That's why it was post-tectonics in the post-tectonic or post-kinematic in the case of first set of deformation. But when you're dealing with D2, that means we are considering the second phase of deformation. With respect to that phase, this particle would behave as a pre-kinematic or pre-tectonic particle. So in that case, it would be having initial fabric, and the later fabric would wrap around it, and the outer ones will be deflected, right, like this. So this is S2, this is S1, and the S2 will be cross-cutting S1, and it will generate granulation. Right, because of the deflection. So this is an overprinting relationship. Right? So which of the following, so in order to interpret or to have or to establish an overprinting relation, we will require, so there are two requirements. First is S1, which is obviously continuous, and host rock should contain the evidence of S1. That means it should be homogeneous, right? So this is the first condition, and the second condition is that S2 deflected around the particle. The third condition is the particle should preserve S1. Right? So that's how we will be interpreting. The thing is that, okay, so there is an overprinting relation. Now the fact that the most important criteria is that the class or the particle, or it should contain, I mean, it should preserve the initial foliations, right? So if the initial foliations are erased, or even in the case it doesn't exist, then it is hard to determine whether there is an overprinting relation already existing or not. So that is why this point is very much important, so that the particle should have a preservation of some sort of foliation, right? And the attitude of the foliation, or the trend of the foliation that we measure from the particle should match with the S1, the signatures of the S1. It should match. Unless there is a rotation of the clast or the particle, but in that case, the rotation can be determined from the deflection of the foliations around it of the second phase, right? So in any case, we can deduce these informations if we have a particle that is preserving the initial foliations. Now, which among the following does that? So we have four options, and amongst that, we can safely say that xenoblast and poikiloblast, they will most certainly contain the fabric information. Blasts, they preserve the fabric information. Right? So whichever is classed, it is a foreign element to the host rock. Or not to the host rock, we can say to the deformed host rock. Right? A clast will therefore behave as a rigid particle which will not contain or preserve the information of the fabric. Clasts do not retain or rather preserve the fabric information. Right? So in that sense, anything which is a clast is most likely to have no signatures of the initial deformation. Therefore, it is much difficult to determine whether there exists any sort of overprinting relation. So we have multiple correct options. A and B both should be correct in this case, because xenocrysts are crystals that are fragmented from the wall rock, and they are uh, consumed or assimilated within the rock. I mean, xenocryst is a term that we commonly refer for igneous rocks, right? Because during magma ascent or fractionation of melt, so this kind of mechanical damage do happen to the wall rock, and in that case, some megacrysts or existing porphyroblasts from the wall rock, they may get plucked out from the wall rock, and they can be assimilated into the magma, and after crystallization we could see relic grains from the wall rock, which are essentially crystals, single crystals generally, and those are called xenocrysts. But whenever you're talking about xenoclast, right, because a blast should essentially be a single crystal of a mineral, because it is growing during or after the deformation within the host rock. It is consuming some elements, trace elements, or major elements through diffusion and dissolution precipitation creep during the deformation from the host rock, and then it is cooking up the crystal while the process of deformation is going on. And during that blastocyst, the blast should, I mean, in more general terms, it should be a single crystal. But Clast may or may not be a single crystal. Clast can be even a polycrystalline aggregate. Clast is essentially a small fragment of rock, whereas a porphyroblast is essentially single crystals. Those are not rocks. But porphyroclast can be a crystal or even a rock. Right? That means it is a polycrystalline aggregate of some minerals. So it is in that sense, xenocrest is most likely to be occurring in undeformed or unmetamorphosed igneous rocks, right? So in that sense, xenocrests are, xenocrests do signify the mode of the mode of origin for that igneous rock, whether it is a plutonic rock or it is an hypabyssal rock, and so on. Right? Because volcanic rocks would not have xenocrests, right? Volcanic rock can have xenoclasts because during eruptive uh, eruptive style of volcanic, depending on the eruptive style of the volcanic magma, that is the lava, eruptive style of the lava, there can be differences in the size of the clast that contains within it. So pyroclastics and volcanic tuffs. So these are the examples of clasts during the occurrence of eruptive volcanism. But whereas xenocrests are essential signatures of plutonic igneous rocks, you can get cumulus textures like large crystals of plagioclase like anorthite and spedific textures in olivine. So those kind of things can occur as xenocrests. So xenocrests are essentially uh, terms most commonly used for undeformed or pristine igneous rocks, which is unmetamorphosed. But xenoclast can, xenoclast refers to a broader range of terms, right? It can range from a single grain of mineral to a polycrystalline aggregate. So even though the both of the answers A and B are correct, so which is more appropriate for the sense that is related to structural geology and the overprinting relationship of tectonic fabrics, I would say option B is much more robust option or robust answer than combining xenocrest and xenoclast. So in that sense, we can say that xenoclasts are essentially such particles that would not preserve any information regarding the overprinting relationship of tectonic fabrics. So this was our first question. So let us move on to our next question. Question number 2. Given below is a schematic diagram showing the relation between the porphyroblast nucleation rate versus time for a given temperature. Right? Which of the following curves given in the option will correctly represent the relation between the mean porphyroblast crystal size and time? I'm sorry, there was a problem in Google Meet, I guess. It crashed. No problem. Okay. Yeah, so as I was telling that, so this is this kind of equation. This is Arrhenius type equation where alpha is basically the transformation factor, or the it simply represents how much reaction has progressed, right? So this is transformation factor, which dictates how much the reaction has progressed. And M is the order of reaction. It can be first order, it can be second order, third order. So the concept is such that, so if I have a space, a surface area or volume, whatever, so nucleation rate means that number of nucleation points per minute per area, per unit area. Per minute, per second, whatever, per second, per unit area. So imagine you have a slow reaction rate. I mean, your reaction is very slow. That means you will have less amount of nucleation points for a given area. Now, if the crystals are starting to grow around that nucleation point, they will get plenty of space to grow. But for the same scenario, if you just increase the nucleation rate, that means at each and every second, the number of points are exponentially increasing. But your overall area is limited. The space you are providing for the crystals to grow after the reaction is limited. In that case, what will happen? Since the crystals will grow around the nucleation point, they will have limited space to grow on, and eventually they will be much smaller in size. So crystal growth, or the size of the crystal, mean dimension of the crystal or the grain size, it generally reduces with the increase in the nucleation rate. So that is why it follows an inversely proportional relation. So because the thing is that now the thing is that you have say an area of 100 micron, for example. 100 micron by 100 micron is your area that you're providing for the grains to grow. Now if you have a very slow reaction rate, that means the amount of energy you are providing to invest after this crystal growth is much less, right? So in that case, what will happen, since you are providing less amount of energy into the system, say for example the nucleation rate, it increases with temperature, right? So if this is the nucleation rate versus time for a given temperature, if I increase the temperature, the curves will merely shift along the y-axis like this. So the nucleation rate increases proportionally to the temperature. Now since we are increasing the nucleation rate, that means the increase in nucleation rate means that we are providing additional amount of energy to to invest that energy in crystal growth. Now how does it make sense that you are giving higher amount of energy to produce smaller grains instead of providing less amount of energy to grow larger grains?
Sir,
This is counterintuitive.
Sir, if we see the solidification of basalt versus granite, as
Yes.
the time changes, granite has enough time to grow, the
Yes.
crystals. But in basalt, this is rapid cooling. Due to rapid cooling, crystal size decreases.
Exactly.
But in this, it is totally inverse.
Yes. So that is why I'm asking that it occurs as very counterintuitive that if we have less amount of energy, your crystals will grow in large size. However, if you have higher amount of energy, your grains will grow to smaller size. That is the concept of nucleation thermodynamics. It tells us that if you have very high temperature and you give sufficiently high nucleation rate, I mean, if you introduce sufficiently high nucleation rate to the system, it would cause very fine grain crystals. So the thing is that despite this counterintuitive argument, the amount of energy that is required to produce small grain size is very much larger than producing larger grain size, is because the energy because smaller grains have higher surface energy per unit volume. Okay, so because if we divide the surface area, say S is the surface area and you have the volume of the crystals as V. So this ratio is much higher for small grain sizes, because if you, for a given area, given amount of volume, if you increase the number of grains, that means you're decreasing the size. So each crystal, the effective surface area of the each crystal, and if you calculate them as cumulative, it will increase compared to larger size grains. So that is the main concept behind crystal growth, and this also causes small grain sized crystals to become more metastable. It reaches more towards the instability, because in equilibrium condition, what will be the uh, natural tendency is to minimize the surface area with respect to the volume, such that it will involve in lesser amount of reactions. So that is the concept. So if you have very high surface area compared to your volume, you will be prone to more reactions, right? Diffusive mass transfer, dissolution precipitation creep, all these kind of things will be more if you have higher surface area compared to the volume. But if you have, I mean, an equivalent surface area compared to your volume for larger crystals or equidimensional crystals. So that is why we call it equidimensional crystals and euhedral crystals, because they are stable. Euhedral crystals are stable. Why? Because their surface area to volume ratio is within the range of its stability. So there is a stability range that we generally refer to as the Clausius-Clapeyron relation, and we can apply this concept of surface energy to volume ratio in the Clausius-Clapeyron relation to establish whether the crystal is actually exceeding its stability field and it is becoming metastable or unstable. So the Arrhenius type equation tells us this relation, that crystal growth actually follows inversely with the nucleation rate. And if I draw a cumulative curve, curve of, say, we have the crystal size in this axis. There are two y-axis, and say this is k, the reaction rate or the nucleation rate. So if this is my nucleation rate increasing with time, we will see that the crystal's growth will follow this kind of curve. So this is a peak crystal size when the reaction rate is much smaller, nucleation rate is much smaller, and as the nucleation rate increases, the crystal size will decrease. So in another sense, whenever we are dealing with basalt, so say for example, we have a granite and we have a basalt. Right? So basalts have very small grain size, right? Why? Because we're quickly quenching the sample. So what does quenching means? Means we are decreasing the temperature in a given amount of time. So talking about temperature, so if I know the mass per unit volume, that means the density of the material. If we know the specific heat capacity of the material, which is C, and we know del T, how much amount of temperature fluctuation has occurred, then this is the amount of heat or thermal energy that is required, right, to change amount of energy, right? Now, if I quickly drain this much amount of energy with very short time, then it is actually meaning that I am increasing my nucleation rate with respect to time in exponential order. So this data, I mean, this equation that is basically telling us about the amount of energy I'm expending or investing to grow the crystals. This amount of energy is fixed. Say we have rhyolite and we have granite. So the amount of energy that is required to increase this much amount of increase or decrease a certain amount of temperature, that amount is fixed. What is changing is the time, how quickly you are changing the temperature. So if you change the temperature very slowly, that means you are maintaining equilibrium condition at every point of time. That would mean your nucleation rate is almost quasi-static with respect to time. So the nucleation rate is not changing. And that is why the grains will get enough time to grow and eventually it will be at larger grain size. But for the same case, when you have a rhyolite and we are quenching the sample, that means we are providing very less amount of time to extract that much amount of energy from the system. In that case, what is happening? We are increasing the nucleation rate, right? And that is why, because of the increased nucleation rate, we are having quenched. Quenched sample means we have smaller grain size. So increasing the nucleation rate can occur in either ways. Either you can increase the thermal energy very quickly, or you can even decrease the thermal energy very quickly. You will get the same result, right? If you have some reactions going on with your sample, say solid solution reaction is going on, it generally takes some amount of time. If you leave it freely, it will be quasi-static. That means you will not be able to distinguish in your daily life. It may require years to happen because it is maintaining a constant equilibrium such that the overall energy remains constant, right? Now, if I perturb any of the parameters, especially the time of the reaction, right? The energy or time. If I perturb these two terms, energy and time, in the system, then what will happen? We will eventually apply or force the system to shift towards an equilibrium condition. So that's the La Chatelier's principle. It tells that whenever there is a disturbance in the system, it will eventually move towards the favorable point such that it will again come to the equilibrium position. So following the La Chatelier's principle, we can again say that if we even increase the temperature very quickly into the system with respect to time, we will get smaller grains. And even so, if we just quench the sample, that means extract the energy, thermal energy from the system very quickly, then we will quench the sample and eventually we will get smaller grain size. So either I am extracting the energy or providing the energy, that doesn't matter. Only thing matters is that how much time is required to do the thing. if I'm giving enough time for the energy to consume or extract that much amount of energy, it will eventually maintain the equilibrium condition at every point of time. But then again, if I perturb with the time and energy, the system will provide a feedback in such a way that it will reduce the grain size to store maximum amount of energy. It will try to retain maximum amount of energy in the form that it will have higher surface energy per unit volume, and eventually it will become unstable.
Sir,
Right? So this, yes.
sir, in this way, we can say that for volcanic rock, as for
Yes.
rhyolite, the
Yes.
if we are quenching the thermal energy, this thermal energy is not dissipated in the environment. It is converted for the nucleation part of it to increase the surface energy.
Exactly. Exactly so. Because when it is being, I mean, it is quenched means it is quickly coming up, like right from a given depth. When it is, I mean, reaching the surface, so it is coming in contact with the atmosphere. Essentially, there is a drastic difference in temperature. So there will obviously be some amount of dissipation involved in this case, right? Because there should be a heat exchange with the atmosphere, because the atmosphere and the lava that is in contact with the air, they will both come in thermal equilibrium to each other, such that the surface temperature of the lava will eventually reach the air temperature. So that is the point, right? So that is but in order to achieve the thing, the more you will the more temperature gradient you are creating into your system, and the more quickly it will try to come into the thermal equilibrium with respect to the environment, that duration will eventually lead to quenching. And exactly so. So the energy for quenching is within the system itself. It is just that because of the difference in temperature with respect to its environment, whether there will be addition of I mean thermal energy or extraction of thermal energy, that will change. But the concept is, if you have much less time but very high energy, the system will try to evolve in such a way that it maximizes its energy input. Sorry, it minimizes its energy input, and to minimize the energy input, it should do some work. The system would do some work to expand the, I mean, to invest that energy, right? So whenever we are quenching, so the system has some energy. So the system or the lava, whatever the component it may be, it will do some mechanical work. And this mechanical work or thermodynamic work is basically creating new crystals, growing new crystals. So this is the work where the system itself is investing the energy. So the dissipation of heat is exactly in the form of mechanical work. It is creating new crystals, but it is occurring beyond its equilibrium limit. That means the duration is not appropriate in this case. It is not maintaining its quasi-static condition, and therefore what is happening, you have a lot to grow, but you have very shorter time, and eventually the area is also, I mean, the volume is also limited. So what will happen? The nucleation rate will increase, because the system has to invest that much amount of energy within the given period of time to come in thermal equilibrium. But the system doesn't have extra volume to maintain its grain size. So what will happen? The system will automatically increase its nucleation rate to come in thermal equilibrium quickly. So that is why when we increase the nucleation rate, eventually the grain size reduces. Okay, so move on to our next question. Which of the following events, if any in possible case, cannot occur during blastocyst of a porphyroblast despite its tectonic nature, right? Transaction of deformation fabric without deflection, transaction of deformation fabric with deflection, option C, termination of deformation fabric with deflection, option D, termination of deformation fabric without deflection. So let me clarify here first. Tectonic nature, I mean, in this case, tectonic nature refers to pre-kinematic, synkinematic, and post-kinematic or post-tectonic occurrence of the porphyroblast. So the blastocyst, that is the mode of occurrence or the mode of origin of the porphyroblast. Is it pre, syn, or post? That is defined through the term tectonic nature. Right? So transaction means it is cross-cutting the deformation. The cross-cutting the deformation fabric. Right? So just let us discuss about what happens in pre, syn, and post kinematic. So say for example we have a clast. If this is pre-kinematic, that means the porphyroblast exist in the system even before the deformation took place, right? So in that case, what will happen? It will not preserve any signatures of the phase of deformation within it, right? So there will be no internal foliations. All the foliations will wrap around the blast. Right? So if I closely examine, the foliations are being terminated at the edge of the blast. So this is porphyroblast. So foliations are terminated at the edge of the porphyroblast. Right? But it is not just terminating, it is deflecting as well. That's how foliations wrap around a blast, right? So pre-kinematic fabric would terminate across the edge of the porphyroblast, but it would also deflect. So the option says, the question says, which cannot possibly occur during blastocyst. So termination of deformation fabric with deflection, this can occur during pre-tectonic blastocyst, right? Now, if you talk about syntectonic, what will happen? Say this is a rigid blast. So the foliations would warp around the blast, the particle, and it would also rotate and deflect inside the porphyroblast, right? So this is basically transecting. So the orientation outside the blast and inside the blast, they may be different because of the stiffness or the rigidity or competency contrast of the blast with respect to the matrix or the host rock. So this is transaction of deformation fabric, right? With deflection. If there is a rotation, right? Sorry, this is the wrong sign. So if there is a rotation, the foliation would deflect, right? So this is how syntectonic blastocysts may occur. So transaction of deformation fabric with deflection. This also can occur during blastocysts, right? Now, if we just talk about post-tectonic blastocysts, in that case, what will happen? It will grow over the foliations. So if these are the foliations, the crystal will grow over that foliation, and that means it will transect, will cut across the porphyroblast, and it will enter and it will exit. The foliations will enter and exit the porphyroblast. That means it will cut across the porphyroblast, of course, because it is post-tectonic, but it will not deflect inside or even outside the porphyroblast, right? So transaction of fabric without deflection. And this thing can also occur during blastocysts. So as in the post-tectonic porphyroblastocysts, right? So only one option is remaining, termination of deformation fabric without deflection. That is the correct answer because it cannot possibly occur for a blastocyst. That means you have a blast. You're seeing that the foliations are being terminated at the edge of the blast, but they are not deflecting. So what kind of thing it is? Even if it is not a blast, even if we consider it as a clast, given its competency contrast and if it behave as a rigid particle, during deformation, uh, this crystal would rotate, this clast would rotate, and eventually you will get termination with deflection, right? If it is if it is pre-tectonic and syntectonic, right? But a clast can never be post-tectonic, right? Sorry, a clast can never be syntectonic. I'm sorry, I'm not telling the correct answer. I guess a clast cannot be post-tectonic because you are having the deformation and then you are,
Post occurring.
incorporating a clast. Yeah.
Post.
After deformation, you cannot even incorporate a clast. So post-tectonic clast cannot occur. Pre-tectonic clast, it definitely can occur. Syntectonic clast, it can also even occur because during deformation, there can be brittle deformation that can incorporate some fragments from the host rock or the wall rock. That is also even okay. But after the deformation, you cannot incorporate a clast within the host rock. And ever since, and even though you can incorporate a clast within the rock, say for example, hypothetically, that even in the post-tectonic situation, you incorporate a clast into your host rock, even though in that case, it will not terminate the foliations like this. So this is an unreal situation. So this cannot practically happen. So that is why option D is correct, that termination of deformation fabric without deflection cannot possibly occur for blasts, even when we are talking about blastocysts, and it is also impossible for porphyroclasts as well. Okay, so let us move on to the next question, question number 4. So since we had practical questions in the week 9 content, so we are actually having some exercises as well here. So the question tells us that a coal bed is intersected by two mine drifts. In one drift, the plunge and trend of the apparent deep is 44 degree towards 066, and in the other drift, the apparent deep of the coal bed is 40 degree towards 344. Use stereonet to determine the attitude, that means the strike and dip of the bed. So even though we do not have the stereonet, but we can closely guess by drawing the stereonet like this. So let us draw a stereonet. If this is north, this is west, east, and south. Okay. So we have 2 points. So plunge is a plunge of the apparent dip. That means we have the linear data. It will represent as a point. So 44 degree towards 066. That means zero six six would lie somewhere around here. So 44 degree means just like this. So we can approximate this point as 1. And the other point is 40 degree towards 344. So this is 270, 300. So this is 330 around. And so this, no, sorry. So this is 270. So 344, I guess, is around closely around this direction. 344. Around this, somewhere around this. So approximately around this direction, and we are having 40 degree. So it is somewhere around here. So if we pass a great circle through this, it will eventually look like this, right? So let us see the options. So which of the options are closely matching? I guess if I mean, this is not 344 at all. 344 would be somewhere around here, I guess. This is 344. This is much appropriate. Okay, so from here we have 40 degree, right? So we can pass a great circle like this. So these are the two ends of the strike, and this is the deep. So which of the strikes are matching? 060 definitely not matching. This end is not 060. It is beyond 90 degree, right?
300.
So this is not exactly. Option C is correct. So this is 300, and since this is 300 and we are having apparent dip 44 degree and 40 degree, so the true dip always be greater than the apparent dip, right? So this must be 50 degree. You can solve this problem in StereoNet to find out. But this is also works pretty well. If you have the idea of StereoNet, how to plot them, then eventually you can get an idea of what will be the dependence type. So this in field, even we in field work, we also even do this kind of exercise, mental exercise, to actually because it is not always feasible to plot your data while sitting on the field in stereo nets, or even using a software in computer or laptop. That's not feasible at all, but we can get a sense just by drawing roughly the stereo nets to get an idea how the beds are oriented, or how the foliations are oriented, and the regional trade. So this was this kind of mental exercise. Okay, so the next question: choose the correct option representing the correct pairing between the following structural features A, B, and C, and their corresponding tectonic timing 1, 2, and 3. They represent A, snowball garnet; B, bent crystal of quartz; C, staurolite crystal overgrowing a foliation, and the counterpart is 1, pre-tectonic; 2, post-tectonic; and C, and 3, syntectonic.
Sir, snowball is syntectonic. Then A and B
Exactly. So snowball, it is definitely syntectonic. So it is A is 3. Now, staurolite crystal overgrowing a foliation. So when this can happen? So if this is a foliation, and overgrowing means you're growing a staurolite crystal like this, parallel to foliation. When it can happen? Of course, it should be post-tectonic, right? Only then this kind of overgrowth can occur. So C, staurolite, it is post-tectonic, which means it is C is 2. So A3B2, A3C2,
option
correct?
B.
Option B, exactly. That means the bent crystal of quartz is pre-tectonic. That is not always true. I mean, this is for the case of this question, we may consider the fact, but bent crystal of quartz,
If it's from
I
if
mean,
if source is already uh, deformed, then it is possible to bend crystal of quartz.
yeah, I mean, bent crystal means you are creating subgrains within the quartz, bent crystal. So creating subgrain itself is a process of deformation, dynamic recrystallization. So that means it may not be related to that particular episode of deformation, but definitely, uh, if there exists a quartz crystal which is bent and there are signatures of prominent subgrains, that means it is not completely recrystallized. It is undergoing recrystallization when the process stopped or somehow it exhumed. So these are the relic grains, and in that sense, yes, because relic grains are often signatures of pre-tectonic fabric. Yeah, because bent crystal means you have subgrain, right? You will see the undulose extinction in the quartz in thin section. Now the thing is that if the dynamic recrystallization process is well complete, right? In that case, you will get turn like this. Okay. So you have to observe the face geometry. Becomes linear, or we can say that uh, the face geometry and this is more competent. Okay. Now, if we observe the geometric classification of Boudins, we will see symmetric Boudins, um, drawn Boudins. So, tone Boudins have linear face geometry, and drawn Boudins have curvilinear face geometry. So, of course, this is more competent, and this is less competent. So, based on this observation, we can say that
B will be.
B is the correct answer, that the drawn Boudins have lesser competency contrast than the tone Boudins. Okay, moving on to the next question, question number 7. Which of the following geometric combination of Boudins is mechanically uncommon in nature? Option A, positive exterior curvature and positive face curvature. Option B, positive exterior curvature and negative face curvature. Option C, negative exterior curvature and positive face curvature. Option D, negative exterior curvature and negative face curvature. Okay. So in the geometric classification of Boudins, we can draw the classification diagram like this. So we have face curvature here and we have exterior curvature here. So in this scale, we have negative this side and positive this side. That means yeah.
I think it's D is right. There is a negative exterior and negative face.
So negative exterior curvature looks like this, and positive exterior curvature looks like this. And here we have negative face curvature and positive face curvature. Again, we have negative exterior curvature, and here we have positive exterior curvature. So in this case, we will have positive exterior curvature and positive face curvature. So the Boudins will almost be like rounded, lobate shape. Here we will have dumbbell shape Boudins. And here we will have spindle, I mean, this kind of shape. So these are the four fields, I mean, four extremities. However, the classification, if you remember, there is a certain field At the neutral point, this is rare, and this is uncommon. So the neutral points in this axis, neutral points and in this axis. So if you join the neutral points in the x-axis and y-axis, eventually you will get the rare and uncommon fields of Boudin structures. So negative phase curvature with negative exterior curvature is extremely rare, but positive phase curvature with negative exterior curvature is uncommon Boudin. But the more common is that we have neutral curvature, that means linear exterior curvature and linear phase curvature, but we can also have positive exterior curvature and positive phase curvature. So just to uh, give example, I mean, you can, if I draw a checkered box, so this is FC and this is EC. Positive, positive, negative, negative. So positive phase curvature and positive exterior curvature is common Boudin. Negative phase curvature but positive exterior curvature is also common. Positive phase curvature but negative exterior curvature is uncommon. And negative phase curvature with negative exterior curvature is rare. So this is how I remember the classification diagram. So in this case, uncommon will be positive phase curvature and negative exterior curvature. Negative exterior curvature and positive phase curvature, right? So the option C is correct. Okay. Question number 8. Choose the correct statement from the given options. The Boudin axis strictly follows the fold axis of for a Boudinage fold. Option B. Asymmetric foliation Boudins develop from sequential tensile fracturing. Option C. Symmetric Boudins are a result of intersurface slip during fracturing. Option D is the inter-Boudinage space results in tensile gash fractures in gash Boudins.
It will be D answer.
Exactly. And why others are incorrect? Of course, it is correct, but why other three options are incorrect?
See, it's not always that Boudin axis follows the fold axis.
Exactly.
It can be different.
Exactly. And asymmetric foliation Boudins develop from sequential tensile fracture. This is also wrong because symmetric Boudins are in fact the results of sequential tensile fracturing, whereas asymmetric foliation Boudins are as a result of intersurface slip during fracturing. So asymmetric Boudin would generate from shear fracturing. Symmetric Boudins, on the other hand, can generate from tensile fracturing. So these are flipped, I mean reversed. So that is why it is wrong. Whereas option D, it is correct because the interboudinous space results in tensile gash fractures in gash Boudins. Okay, moving on to the next question. What is the critical aspect ratio of a Boudin? Option A, aspect ratio of each Boudin that is independent of the initial length of the intermediate layer. Option B, aspect ratio of each Boudin that depends on the competency contrast of the intermediate layer. Option C, aspect ratio of each Boudin that depends on the critical thickness of the competent layer. And option D, aspect ratio of each Boudin that depends on the critical thickness of the incompetent layer.
Sir, see, it is depend upon the competent layer, because as
Exactly.
small buddings are thinner and large buddings are thinner.
Exactly. So, the critical aspect ratio AC is defined as the aspect ratio for a certain thickness of the competent layer. So what is aspect ratio? Basically, it is the length by thickness, right? So this is the aspect ratio of the Boudins. So aspect ratio for a certain thickness of competent layer, uh, beyond which not beyond, I mean below which, not beyond, below which the competent layer cannot be segmented into two parts. Competent layer cannot further be segmented into two parts. So this is the definition of critical aspect ratio. So that means if we have very thin or very thick layer, very thin or very thick, it would always be restricted to its length. I mean, if we have the length of the Boudin, I mean, if this is the thickness D and this is the length L of a Boudin, so for example, of a layer, in competent layer, and we are applying the tensile forces, the tensile stress parallel to the length of the given Boudin. So in this case, what would happen? It is very difficult to fragment this Boudin, whereas if you have a very thin layer and then we apply the tensile stress, it is easier to fragment it into two parts. Right? So critical aspect ratio will be governed by the thickness of the competent layer, because thickness times the aspect ratio will be the length of the Boudin, right? So given a certain length and a certain thickness, the aspect ratio will be determined how much stress is required to generate newer segments from the given layer. Okay, so question number 10. If x, y, and z corresponds to principal axis of strain, then choose the condition most likely that would result in formation of folded chocolate tablet Boudinage in a single deformation event.
Sir, this
So
will be C.
C, exactly. Option C is correct.
I
So
have
to describe that, yes,
I have
yes,
already anticipated this question.
okay. So the reason behind is that, so if we have a fold in the flattening field, right? So in the Flynn diagram, We have the y-axis k is equal to infinity, we have x-axis k is equal to 0, and we have the plane strain condition where k is equal to 1, right? So this is the Flynn diagram, and here we have constriction,
बहुत अच्छी है.
and here we have flattening, right? So in case of flattening, we have the situation x is equal to y, which is greater than 1, and is of course greater than z. And generally, we represent Boudinage fold in case where x is greater than 1, y is equal to 1, or greater equal to 1, and z is less than 1. So this is the situation where we have stretching along the x-axis much larger than the y-axis, and we are getting the segmented or Boudinage gleam. Now imagine you put so much stress along this direction that you flattened out the strain ellipse like this. So eventually you have already extended x, but now you are also extending y, but x is very, very greater than y. No, sorry, very, very greater than 1, not y. And eventually y is also very, very greater than 1. So if you have extreme flattening where x and y, both the directions are extended. So you are now extending y, the ratio such that it is exceeding the value of 1. You have already created the fracturing, tensile fracturing along the limbs, while you have extended the x and you have made the strain ellipse like this. Now if you flatten it out, eventually it will happen such a condition that both x and y, they have exceeded 1, and it is completely oblate. So what will happen? You will also start creating fractures along y. I mean, sorry, perpendicular to y, right? And eventually you will end up producing this kind of fragmented structure. These are chocolate tablet. I don't know why they call it chocolate tablet. But anyway, so this is how the strain ellipse condition would satisfy the formation of a folded chocolate tablet Boudinage. Because in forming chocolate tablet Boudinage without a fold, it would satisfy this condition. Simple flattening. X equals to y, which is greater than 1, and of course z is less than 1. But if you have folded chocolate tablet, that means you are also flattening, creating a fold through flattening. That means it would obviously exceed the value of 1. Okay. Next question. A bed has a strike of 250 and deep of 40 towards north. Plot pole to the plane using stereo net and choose the correct option. So it is quite easier. So bed has a strike 250 and deep 40 towards north. So 250 would generally lie like this, right? So this would be the bed. This is 40. close to north, not directly north. It would be around 340, the deep direction, right hand rule. Now to get the pole, so you will have exactly opposite end of this trend, right? So the trend is 340. The 180-degree opposite end will be 160, right? So to get the pole, you will have the reverse strike end. And pole means it creates 90-degree with respect to the plane. So if this is a plane, so pole is the vertical to the plane, which maintains a 90-degree. So that means 40-degree already here. We need another 50-degree. So imagine we counted 40-degree from here, and then you go on the other side, and then again you start counting from 0 to 50. So you will end up having here. So this will be your pole. The pole will be having a plunge amount of 50-degree, and which will be trending towards or plunging towards 160. Right? So how 340 was determined? Since this is 250, so according to right hand rule, you add 90, you get 340. So the opposite end of 340 is 160. You just subtract 180 and you get 160. And this is the deep amount. So the pole will be 90 minus the deep amount, 5. So this is 50-degree towards 160. So option C is, option B is correct. Yeah. Okay. So moving on to our last question. In an outcrop, a symmetrical synform is exposed. The attitude of the two limbs of the synform is 340-degree northeast and 030 50-degree east. With the help of stereonet, plot the attitude of the limbs and choose the correct options. Okay. So we have to draw the stereonet first. So the two limbs are 340-degree northeast. So this is most likely this is 300. This is 120. 40-degree northwest means will be like this. And the other limb is 030 50 east. So this is 030 50-degree east. That means it will be steeper bit. So this will be so this is the intersection point of the two limbs, right? So of course it is not lying on the periphery. That means the fold is plunging. So we can quickly eliminate these two options, A and B. So we have remaining two options, C and D. The fold is of course plunging. So now if we just pass a great circle from this intersection point, we will see that the axial plane has a very high dip. Right? not like this. We can say the axial plane is going like this. Somewhat like this. So this is the axial plane. So the axial plane will have much larger dip. That means the axial plane is steeper.
Steeper. Sir, C is already disqualified because if it is horizontal, then it will be in periphery.
Exactly, yes. So the axial plane, any axial plane which is horizontal cannot have plunging fold. So that is automatically discouraged. Yes, exactly. I just saw the last word written as plunging, non-plunging. So I thought that option C is considering plunging fold. But now I see that option C says that the axial plane is horizontal. That means it is a recumbent fold. Right? So in that case, there won't be any plunge amount. So that means it's a neutral fold. So of course, option C is eliminated, and eventually option D is correct. Exactly. So the axial plane is steep and it is plunging. The fold is plunging. Okay, so this was all about today's
Sir,
discussion
sir,
session. Yes.
any two
Yeah.
lines of topic intratectonics. Uh, we
Intertectonics.
we have studied pre-Sen and post-tectonics. Some Boudinage
Okay.
developed during intertectonics. What are their characteristics during intertectonics?
Intertectonic, I mean, intertectonic period, I mean, between two deformation events, there are some. The thing is that any sort of crystal growth which is occurring between two deformation events, it is very much difficult to actually comment whether these, I mean, porphyroblasts, they are intertectonic or they are showing overprinting relation, because the moment there will be another phase of deformation, the whatever signatures that were in the porphyroblast, it would be
Obliterated.
overprinted.
Or
Overprinted. Now the thing is that post tectonic porphyroblasts can actually serve as intertectonic porphyroblasts. So in the first question, I have discussed this topic, is that which of the following microstructural feature does not provide any information regarding tectonic overprinting of fabric? Now, if I have, say, a post-tectonic uh, porphyroblast, right? So if it grows post-tectonic, the foliations or the fabrics will easily transect the grain and there will be no deflection, right? But if another set of deformation, say D2, which is non-coaxial with respect to D1, that means it is at an oblique angle to the, I mean, the foliations S2, they are at an oblique angle to S1. Consider this situation. So what would happen? The grain, the foliation inside of the grain, they would show straight, I mean, straight foliations without any kind of deflection or rotation. But since with respect to D2, the particle will behave as pre-tectonic, right? Because it is not growing during D2. It is already there when the D2 is taking place. So what would happen? The second generation of foliations, S2, they will wrap around the existing particle, and it will create granulation cleavages around the around this porphyroblast, because there was an existing S1 and now there is a perpendicular S2, so their superposition would definitely result in granulation. So we can get a microstructural feature where foliated porphyroblast is embedded within a granulated host rock. and the S2 is largely deflected around the foliated porphyroblast, and there is no connection whatsoever with the orientation of the internal fabric and the exterior cleavage. And this uh, can to some extent represent a sense of intertectonic porphyroblast, because it was pre to the previous deformation, post kinematic to the previous phase of deformation, but it is pre kinematic to the second phase of deformation. It is occurring in between these two events. So this kind of microstructural feature may preserve some evidences of intertectonic porphyroblasts.
Thank you.
Okay, so thank you for joining today's class. And for the week 10 and week 11, I guess I will be conducting a field work, so I have to prepone or postpone the classes. So I will write to NPTELs to change the date of the class. So it is that I will be taking this 11th week's class not on 5th September, but before that date. So eventually you will get an email from NPTEL. Okay. Thank you. So let me close today's meeting.
Thank you.